Hey folks, welcome to another set of AP Chemistry video notes. Today we're going to cover topics 2.5, 2.6, and 2.7. The overall goal for these three topics is for you to understand that the arrangement of molecular compounds is based on Lewis diagrams and the Vesper theory. These three topics ask you to be able to represent a molecule with a Lewis diagram, do so in a way that accounts for the resonance between equivalent structures, or that uses formal charges to select between non-equivalent structures, and based on the relationship between Lewis diagrams, Vesper theory, bond orders, and bond polarity, explain the structural and electron properties of molecules. Let's get started. I hope you remember how to draw Lewis diagrams from your last couple of years of chemistry, but let's review just in case. A Lewis symbol consists of a chemical symbol for an element surrounded by one dot for each of its valence electrons. Remember, the valence electrons are only those in the highest principal energy level. So for magnesium here, with an electron configuration as such, we'd say it has two valence electrons since there are two electrons in the third energy level. When we draw the Lewis symbol, we try to space out the electrons as much as possible, but we're usually limited to just four regions around the symbol: the top, the bottom, the left, and the right. The Lewis symbol of magnesium would look like this. Phosphorus has 5 valence electrons, so you'd place one electron in each region, but then pair the fifth one up with one of the first 4 electrons. At most, you should only ever have 8 electrons in your Lewis symbol. We can also use Lewis symbols to illustrate how an atom forms a cation or an anion of itself. Let's use the examples we just made. Magnesium has 2 valence electrons. Being a metal, it's going to lose those electrons to form a cation. So on the left side of our reaction arrow, we have the Lewis symbol we just drew. On the right side, we write Mg with a 2+ charge because it lost 2 negative electrons. Notice we didn't draw any electrons around the symbol now. Those electrons didn't just disappear, we have to account for them by writing 2 electrons into the products on this equation. We could do the same for phosphorus. Being a nonmetal, phosphorus would rather gain electrons than lose them. Remember, the ultimate goal is to get to 8 outer electrons, so since it originally has 5 valence electrons, phosphorus needs to gain 3 more. Start by drawing the Lewis symbol for the phosphorus atom. Then, since we're adding electrons, we'll account for those on the reactant side. On the right side of the equation, we have the Lewis symbol for the 3 negative phosphorus ion. Notice that it has 8 electrons around it now. Lewis symbols may be a piece of cake, but Lewis structures are a piece of pie. Lewis structures describe the bonding between atoms in molecules or polyatomic ions. For binary molecules, or 2 atoms, they're super easy. For covalent molecules like chlorine, you just write the 2 symbols down, put them together in a way that the lone electrons in one atom pair up with those in the other, then replace that shared pair of electrons with a bond. Ionic compounds are a little different. Since the electrons are not shared, you will not be replacing any of them with bonds. You could, however, draw the Lewis symbols of the atoms, draw arrows to show the electrons moving from one atom to the other, then show the ions next to each other with their new ion Lewis symbols. For example, the Lewis structure for magnesium oxide would look like this. You should follow these steps to draw Lewis structures of covalent molecules of more than 2 atoms. First, find the total number of valence electrons by adding up all of the valence electrons from each atom in your molecule. If you have a polyatomic ion instead of a molecule, you'll need to subtract 1 electron from your total for each positive charge on the ion, or add 1 electron to your total for each negative charge. Next, choose which atom will be your central atom. This is usually the least electronegative of the atoms, but never hydrogen. Write that atom down, arrange the other atoms around it, then connect those outer atoms to the central atom with single bonds. You have now drawn your skeletal structure. Those single bonds you just drew represent 2 shared electrons each. So now you have to subtract 2 electrons from your total for each bond that you drew. This gives you the amount of electrons you have remaining. Place those remaining electrons on the outer atoms first, again, not hydrogen. You should do this in a way that completes octets. In other words, don't put more than 8 electrons on each of those outer atoms. Each atom already has 2 electrons since you just put bonds there, so you don't need any more than 6 lone electrons on those outer atoms. If you run out of room on your outer atoms, move on to the central atom and keep placing electrons. When you've placed all of your electrons, evaluate your structure. Does each atom have 8 electrons around it? If not, turn some of your lone pairs of electrons into double or triple bonds. Your ultimate goal is to fill all octets. If you don't remember, the octet rule basically says that our main group elements tend to gain, lose, or share electrons in order to have 8 valence electrons. There are, of course, some exceptions to this rule that you need to keep in mind while creating Lewis structures. Hydrogen follows the duet rule, which means it only wants 2 electrons. Some elements can form incomplete octets, which form electron-deficient molecules. Elements in groups 2 or 13 tend to do this if they're the central atom in a covalent molecule, and if they're attached to atoms that only form single bonds. On the flip side, some elements can form expanded octets, which form hypervalent molecules. Any element that has a d orbital, so any element in period 3 or greater, can have more than 8 electrons when it's the central atom. This is because those d orbitals add a layer of maneuverability to the electrons, so some funky things can happen when these elements form bonds. Let's do an example. To draw the Lewis structure of CHO2 negative, add up the number of valence electrons for each atom, then add 1 additional electron for the negative charge. This gets us to 18 total electrons. Next, pick a central atom. Hydrogen can't be it, and oxygen is more electronegative than carbon, so carbon must be our central atom. Draw the skeletal structure with carbon as your central atom. Don't forget the brackets with the charge around it. We just used 6 electrons for our 3 bonds, so subtract that from our total 18. Now you place those remaining 12 electrons on the outer atoms, but remember, hydrogen already has 2, so it's happy. So you need to place those electrons on the oxygens. Next, evaluate your structure. Is each atom happy with the number of electrons it has? Right now, carbon only has 6 electrons, so to give it 2 more, we can turn one of oxygen's lone pairs into a double bond on the carbon. Now, each atom has 8 electrons around it, and we have a valid Lewis structure. We can often create more than one valid Lewis structure for a molecule. Just because it's a valid structure doesn't mean that it's a favorable structure, which we'll see here in a minute. When you have Lewis structures that are equally favorable to each other, we call them resonance structures. When this occurs, we have to account for each of these resonance structures in order to accurately predict the structure and properties of the molecule. It's important to know that these structures are not actually distinct from each other and do not individually represent what the molecule looks like. Instead, the molecule forms kind of a hybrid or average of those structures, with bond lengths that are somewhere between what you'd expect on either of the 2 resonance structures. You may have learned at some point that it's appropriate to write these structures with partial bonds to show that they're resonant. That's not okay with AP Chemistry because you have to show that you understand that each of those resonance structures play a role. You have to draw each individual structure and not attempt to draw the average structure. When we have valid Lewis structures that are not equivalent, we can determine which one is the best model by looking at the octet rule and formal charges on each atom. It's also important to know that Lewis structures are only so useful. When we have an odd total number of valence electrons, we're bound to end up with something called free radicals, or just lone electrons that aren't paired up with any other electrons. This is something that occurs and that you need to be aware of. Let's take our last Lewis structure for example. We could have easily drawn that with the double bond on the oxygen on the top or on the oxygen to the right. These are considered resonance structures to each other. If they were distinct structures, you'd expect the double bond to be shorter than the single bond. As it turns out, the actual molecule has a bond length that's somewhere between the 2. The electrons get equally distributed, not stuck in distinct single or double bonds. So if you're given data on the length of a normal carbon-oxygen single or double bond, and asked to predict the bond length of this molecule, you'd estimate an average bond length between those 2. Formal charges are not real charges. Make sure you understand that. They represent what the charge would be if you gave all of the electrons around an atom to that atom. It's merely a bookkeeping system that helps us determine our best Lewis structure. To find the formal charge on an atom, take the number of valence electrons the atom would have on its own, subtract the number of lone pair electrons the atom has, Then subtract 1 electron for each bond the atom has. Once you've assigned formal charges to all atoms, you can double check your work by adding up all of the formal charges together. The total should equal 0 for molecules. For polyatomic ions, the formal charges will add up to equal the overall charge of the ion. After assigning formal charges, you can determine which Lewis structure is most favorable. That Lewis structure helps us determine the molecular structure, or the way the atoms are bonded and arranged in a molecule. The most favorable structure is one that fills all octets appropriately. From there, the most favorable is one in which each formal charge is 0. If that's not possible, then the most favorable structure has the least amount of non-zero charges. If you have non-zero charges, it's more preferable to have them spaced out, or if they're next to each other, they should be opposite charges. Lastly, if none of that helps you narrow it down, look at where those non-zero charges are placed. The structure with the negative formal charges on the most electronegative elements will be more favorable. Let's do some examples of this. For our first example, we have 3 possible Lewis structures for CO2. Oxygen normally has 6 valence electrons. If we subtract the 4 lone pair electrons and 1 for each bond, that gives us 6 minus 4 minus 2, which gives us 0. Same for the oxygen on the other side. Carbon normally has 4 valence electrons. If we subtract 1 for each bond, that's 4 minus 4 gives us 0. We can already tell this is a very favorable structure. All of the octets are met, and each of the formal charges are 0. The next one's still a valid structure, though, because all of the octets are filled. If we were to assign formal charges here, we'd get +1, 0, and -1. This is less favorable than our first structure. This third one probably isn't a structure you'd come up with following those steps for drawing Lewis structures, since carbon is not the central atom here, even though it is the least electronegative. Assigning the formal charges gives us +2, 0, and -2, which just shows us how much more unfavorable the structure would be because we didn't put carbon in the middle. We already have the formal charges for this next one. Notice how the total of all the formal charges on each of these polyatomic ions adds up to -1. That's because that's the charge on the ion. So which do you think is more favorable? Well, again, that would be the first one here. This one has the least amount of non-zero formal charges. Okay, now that we know how to find the most likely structure of a molecule, we have to know how that affects its shape and bond angles. The valence shell electron pair repulsion theory basically tells us that since the electrons all have a negative charge, they experience Coulombic forces of repulsion against each other. The electron regions around the central atom like to spread out as much as possible in order to alleviate their repulsions. Remember, Coulomb's law says the further apart they are from each other, the less force they feel from each other. So this leads us to 5 predictable shapes for our electron geometries. If there are 2 electron regions around the central atom, we have a linear shape with a bond of 180 degrees. 3 regions gives us trigonal planar with a bond angle of 120 degrees. 4 regions is tetrahedral with bond angles of 109.5. Trigonal bipyramidal occurs when there are 5 electron regions. The axial regions, the ones on the vertical axis, have a bond angle of 180 degrees from each other and 90 degrees from the equatorial plane. The other 3 electron regions exist on a horizontal plane called the equatorial plane and have bond angles of 120 degrees from each other. Lastly, if we have 6 electron regions, we'll have 2 in the axial position and 4 in the equatorial position, but they're all spread out to be 90 degrees from each other. This is called octahedral. From there, we can start thinking about the molecular geometry of our molecule. The molecular geometry is only concerned with the shape the bonding electrons take compared to each other. This is only different from the electron geometry if some of our electron regions are non-bonding regions of electrons, otherwise known as lone pairs of electrons. When that's the case, our bond angles change a little. In terms of how strongly electrons will repel each other, lone pairs of electrons repel other lone pairs of electrons with the most force, followed by lone pairs of electrons repelling bonding pairs of electrons, and then lastly 2 bonding pairs will repel each other the least. Therefore, like you see in this molecule, our lone pair of electrons here is repelling the other bonded pairs of electrons, giving us a bond angle of less than the 120 degrees that we had when they were all bonding electrons. I'll give you a copy of this chart for now, but you need to understand why this happens, and you need to memorize these shapes and bond angles, as you won't be provided with them on the AP exam. You can also think about this as the amount of space the electron region will take up. The more space an electron region takes up, the more they can push other regions further away. Lone pairs take up the most amount of space, followed by triple bonds, double bonds, and lastly, single bonds. To determine the molecular geometry of a molecule, you have to determine the Lewis structure first, then count the number of electron regions to determine the electron geometry, and from there look at how many of those regions are lone pairs around the central atom, and then determine the molecular geometry. You'll notice on the chart, but these molecular geometries place the lone pairs in the best position to minimize their repulsion. For example, for a 5-electron region molecule with one lone pair, that lone pair is best placed on one of the equatorial positions. If you place it on an axial position, it'd be 90 degrees from the 3 equatorial bonding positions, and then 180 degrees from the other axial position. When we place it on one of the equatorial positions, it's able to push the other 4 regions out, and then it's a little over 120 degrees from the other 2 equatorial positions, and just a little over 90 degrees from the 2 axial positions. This puts those bonding regions a little further away than when the lone pair was put in the axial position, minimizing the forces of repulsion. In our last set of notes, we talked about the polarity of individual bonds. You need to know how to determine that and how to determine the molecular shape in order to figure out whether the whole molecule is considered polar or not. To refresh your memory, the polarity is determined by the difference in electronegativity between the 2 bonded atoms. A larger electronegativity difference means a greater polarity. You learned that the partial negative charge goes on the more electronegative element. The dipole moment would be drawn pointing towards the atom with the partial negative charge, and it would be relative in length to how big the difference in electronegativity is. If you have more than 2 atoms, it's a bit more complicated. You need to draw the molecule in its approximate shape first. Assign the dipole moment vectors to each bond, making sure they're pointing in the right direction and are relative in length to their electronegativity differences. If you know how to do vector addition, that'd be really handy right now, but if not, just imagine these vectors in a 3-dimensional space and analyze which way they're pointing in all 3 dimensions. It might be easiest to analyze them 2 at a time and try to combine them as you do so. Look for dipole moments that are equal in magnitude and pointing in opposite directions. This often happens when the central atom is bonded to 2 identical atoms. Since they're pointing in opposite directions and they're the same length, they would cancel out. If they're pointing in the same direction, they would add together though, not cancel out. When 2 dipole moments add together, you could think about that as one larger dipole moment pointing in that same direction. Sometimes they'll cancel out maybe horizontally, but they could both be pointing up a little bit. This would give an overall dipole for the molecule that points up. If you don't have an overall dipole because all of your dipole moments cancel out, your molecule is nonpolar. If you do have an overall dipole because some dipole moments didn't cancel out, your molecule is considered polar. Let's look at a couple of quick examples of this. Here we have carbon dioxide and water. The dipole moments on carbon dioxide are pointing in opposite directions because this molecule is linear. They are of equal magnitude because they both involve a bond between carbon and oxygen. These vectors would cancel out, leaving us with no overall dipole and a nonpolar molecule. Water, on the other hand, has dipole moments that both point in towards oxygen. These dipole moments would cancel out horizontally, but they both point slightly upwards. This gives us an overall dipole that points up, making water a polar molecule. As you should know, the electrons in atoms exist in regions known as orbitals. You've seen these when we talked about electron configuration, but now we have to talk about what they look like when bonding. In order to understand molecular orbitals, which are the electrons that participate in bonding, you have to know our atomic orbitals. Each individual suborbital only holds 2 electrons. The s orbital only has 1 suborbital, and it's spherical shaped. The p orbital has 3 dumbbell-shaped suborbitals, each residing on the x, y, or z axis of the 3-dimensional world. The d orbital is a little more complicated with 5 possible suborbitals, and f is just out of this world with 7 suborbitals. We really only need to focus on s and p orbitals for now. The valence bond theory says that covalent bonds are just an overlap of the orbitals from each atom. These orbitals only have one electron in them, and that's why they're overlapping with another orbital. The bond is just an attraction between the nucleus of each molecule and the lone electron in the other. This attraction forces the orbitals to overlap. The more overlap the orbitals have, the stronger the bond is. Sigma bonds are formed anytime two s orbitals or an s and a p orbital overlap. This also happens when two p orbitals overlap end to end, as pictured here. If you were to draw a line between the two nuclei, you'd see the internuclear axis. As long as the orbitals overlap across the internuclear axis, it's a sigma bond. Sigma bonds allow for a lot of overlap, so they're much stronger than pi bonds, which form when p orbitals overlap side by side. The pi bond creates a node, or a plane, where there's no probability of finding an electron. This node exists along the internuclear axis, so there are no pi bonding electrons between the two nuclei. This makes a pi bond weaker than a sigma bond. To translate what we just learned about Lewis structures to what we're learning now, all bonds, whether single, double, or triple, have sigma bonds. Since sigma bonds are stronger, those will be the first to form. You can only have one sigma bond between the nuclei because more than one orbital won't want to occupy the space between the two nuclei. Pi bonds, though, occur outside of the internuclear axis, so there's room for them. When you have one pi bond along with your sigma bond, that's a double bond. When you have two pi bonds around your sigma bond, you've got a triple bond. It's reasonable to assume that the atomic orbitals of two atoms would just simply overlap and boom, you've got a bond. Unfortunately, things aren't quite that easy. Anytime your atom bonds to another atom, its orbitals will hybridize. Instead of the picturesque orbitals we think of when we do electron configurations, the s and p orbitals merge together to create hybrid orbitals that have slightly different shapes and energies from their original. Some things to note about hybrid orbitals: they only happen when the atoms are covalently bonded, not when they're just hanging out being atoms. The hybrid orbitals are oriented differently and have different shapes than the atomic orbitals that they came from. The number of hybrid orbitals you produce is equal to the number of atomic orbitals you had to combine together to create them. All of the orbitals in a set of hybrid orbitals will have the same shape and energy. There are three types of hybrid orbitals, which we'll learn about in a second, but those different types are dependent on the electron geometry of the molecule. And lastly, the hybridized orbitals will overlap to form sigma bonds, but pi bonds are only formed by unhybridized orbitals. Okay, I know you're just itching to see these in action. There are three types of hybrid orbitals: sp, sp2, and sp3. Sp hybrid orbitals are formed by combining a p orbital and an s orbital together. You can imagine moving one of these electrons from the 2s here up to one of the two p orbitals. Those two half-filled orbitals will hybridize together to create two new sp hybridized orbitals. Notice the two sp orbitals in the energy diagram. They have the same amount of energy. Visually, it looks like this. Our s and p orbitals combine together to create these two sp orbitals, which arrange themselves in a linear fashion. Same kind of deal with sp2 hybridized orbitals. One of our two s electrons will jump up to occupy one of the empty 2p orbitals. Then they combine together to create three sp2 orbitals, all at the same energy. These orbitals look similar to our last ones, but since there are three of them, they arrange themselves in a trigonoplanar shape. Lastly, you can guess what happens in the sp3. These four orbitals will come together to give a tetrahedral shape. To figure out what hybridization your atom has, first draw the most favorable Lewis structure, then determine the number of electron regions around the atom in question. Based on that number, look at this chart to determine the set of hybridized orbitals that will occur. Alright, I've taken enough of your time on this video. Please make sure you read the 6 suggested sections in your textbook, especially sections 5.2 and 5.3, which talk about how these hybridized orbitals look when bonding. You can skip the parts about sp3d and sp3d2 hybridization, as the science isn't quite settled on that yet, and it will not come up in the AP exam. With that said, that's all for today, folks. I hope this video helps you, and as always, if you have any questions, please ask.